Yeah, happy to stay a little bit afterwards and chat with y'all. I know some of y'all tried on Tuesday and there was a bit of a line, but yeah, we can chat a little bit, but I will need to get going eventually. So, all right. Let's see. So unfortunately on Tuesday, Google Meet kind of stopped after 15 minutes. I guess I should plug this in. I thought it was plugged in. And terminated. I actually got a transcript, which I might upload, but I didn't get a recording. And even if I had, it would have only been 15 minutes long. So I'll try to keep my eye out on this thing to make sure it doesn't do that again. But yeah, so I sent out a couple of emails. One was just saying that, yeah, I'm here. And the other one is giving you some information about the present homework assignment, right? So, and yeah, and then so that assignment is on that root raised cosine filter and some channel effects and that type of thing. And then that's due, I think Tuesday, maybe Tuesday at midnight. Then we'll have our little Easter break, but I will release an assignment on this error control coding that we will talk about. I'm still not getting. Is that the right button? It just worked last time. Yeah, okay, there we go. All right, so today let's talk about, let me make sure that is recording, and let's talk about error control coding, right? So we'll talk about the concept, we'll look at some channel models, and talk about how in a lot of situations our communication systems are formed into packets of information. I think probably in embedded systems you might have looked at like parity check codes or something like that when you're sending data around in an embedded system. Maybe not. I know when I taught it, I included that information. So it's very similar. And then we'll dive into block codes in particular. And then in the next session, we'll look at convolutional codes. All right. So we've seen this diagram before, right? And now we're finally going to focus on this channel encoder and channel decoder. And here we're adding redundancy in a structured way to cope with errors in the channel, right? And the channel is not perfect. It introduces errors which can occur distributed over time. And this is an important thing to reflect on and kind of study as you design an error control coding strategy for your system. Do you expect errors to be randomly distributed in a sequence of symbols or bits, right? Or might they come in burst where you might have a whole bunch of bits wiped out and then have good transmission and then maybe another burst, right? So that might be comparing a channel that's just dominated by additive white Gaussian noise, which is pretty random, versus maybe something that's due to interference or maybe some shadowing or cancellation via interference when you might drive or walk behind a building or a wall or just into like a dead zone of a cell system or a Wi-Fi or whatever. Then your errors are going to increase quite a bit, right? So then We have our channel decoder. Its job is to estimate the original bits that were sent into here, right, from what it's receiving. And it's relying on some redundant bits and some structure associated with those redundant bits. Okay. So a channel model is normally a statistical model of the channel, and it's essential to creating an effective coding technique. We're going to focus on the binary symmetric channel, often referred to as BSC. And in this case, the input and the outputs are bits, right? And so they're either 0 or 1. And the channel, the imperfections of the channel may cause or will cause a 0 to be transformed to a 1 or a 1 to be transformed to a 0 with equal probability. And we'll denote that with P, right? So the channel could translate a 0 to a 1 or a 1 to 0. And we're going to consider those equal probable, right? That's where the symmetric part comes in, independent of transmission at other times, right? So each transmission is independent of other transmissions. And note that the channel is often not reciprocal, but we won't really go into a whole lot of that worries. So now many digital communication systems, form up these bits, they form up these symbols, and then we'll send that as a packet. That packet will then have, like at the beginning of it, it'll have maybe a set length, or it might have a variable length, but the header, the first few bits you're sending, will have things like what kind of packet it is, but also what the length of the packet is, right? And then it will often have some parity check bits in it, and that might be kind of a unique calculation of all the bit values or all the symbol values in that packet, and then you'll be able to check it to see, hey, was there an error in this packet or not? So what ends up happening is that we might have we might be calculating our bit error rate. So now we're going all the way back to the beginning of the communication system and the very end of the communication system, where the data is still represented in bits. And we're going to compare those and make sure. Okay, good. We do have someone joining here, so I was worried that it was going to error out on me, so timeout on me. So we can also measure symbol error rates, right? So that would then be, we're kind of comparing the output symbols versus the input symbols. And if we have a K of 3 or 4 or something like that, then our bit error rate and our symbol error rate are going to be related to that. Note that if you have, let's say, a K is equal to 3, right? So we have 3 bits per symbol. Then if we have an error in a symbol, well, that whole symbol is bad. But if we reduce it down to bits, there may be like 1 or 2 or 3 bits in error, right? So our symbol error rate and our packet error rate are going to have some relationship to each other through that K value. But now we can also talk about a packet error rate. So at sometimes around the, well, I'll talk about that on this slide, I guess. So we're going to talk about now forward error correction, often just pronounced FEC. Okay, uses codes to correct a certain number of errors in that packet or in that sequence of transmissions. Then we'd like to be able to, once we receive some symbols, to be able to correct it using the information that's already been provided. But sometimes we can only detect that there was an error, right? And maybe there's been too many errors to be able to figure out how to correct it. But we can determine that there was some errors in that transmission. Now we can ask the transmitter, hey, go ahead and send that packet again, right? So do you guys study like TCP and data communications, or is that only computer engineers? Yeah, so you did study, okay. Oh, okay, yeah. So TCP and IP, they have this, TCP has this acknowledgement type of thing, right? Where if it times out or detects that there's a bad packet, it can it'll have a retransmission. So we're doing the same type of thing here, right? So we would call this sometimes automatic repeat request, or ARC, and resends a packet if it has not been acknowledged or acked by the receiver before some timeout, right? And a hybrid ARQ or HARC, these are become very common in like 5G cell phone communications and Wi-Fi and that type of thing. It's combining both of these techniques, right? So there's some actually a whole kind of hybrid conglomeration of different forward error control, forward error correction coding. And so you're trying to get it to be able to correct on the first go, but then there's this kind of other kind of wraparound process that will manage kind of a retransmission. So these type of things occur at higher layers of the network stack. All right, so by transmitting extra bits, we can detect and sometimes correct errors at the receiver. In general, you can, for a given code size and structure, you can detect more errors than you can correct, right? So you might be able to correct in a certain length of symbols that you might be able to correct one error or two errors, but you might be able to detect maybe 3 or 4 errors, right? And all. So it's the structure in the code that helps the decoder, right? So let's define the code rate. Now, this is an important metric when we talk about codes. So we'll let K and all right, so there's we have to be a little bit careful because we've already used K before, right? And M-area modulation, and it's normally going to be related, but just be careful when you look at some of this notation, right? But K be the number of input bits, and then N be the number of bits in the code word. All right, so what we're going to do is we're going to take K bits coming in, and you remember how we took K bits and then created a symbol out of that for M-area modulation. Now we're actually going to take, before we get to that modulation stage, we're going to take K bits and we're going to create a code word of N bits, right? Where N is typically larger than K, right? Otherwise we're losing information, right? So we will define code rate as this ratio, K over N, right? So our code word needs to include all original data plus some redundant bits. So N is going to be larger in K in general. So this ratio of K over N is going to be less than 1. And we can also denote it in this N comma K type notation, right? So lower code rates are going to take more bits. Okay, so N is going to be larger and to a degree more symbols and overall time to transmit to be able to communicate, right? but they are more powerful. We're including more of these kind of redundant bits to allow us to be able to maybe correct errors at the receiver rather than the very expensive process of having to tell the transmitter, hey, resend that data, right? So that's a very expensive process. You're having to transmit the whole packet again. Instead, boy, if we can, let's correct it when we receive it, right? So there's this trade-off, right? But it can be effective when the alternative is having to retransmit a packet itself. So code rate is one metric of describing a code. Then we have distance, or in particular, we'll call it the Hamming distance. You know, it's named after someone. So we denote that with the lowercase d. It's an important measure of how effective the code will be at detecting and correcting errors. So if you know d, you can go a long ways to determining how many errors a code will be able to detect or correct, right? So, and what this is it's the total number of differences between two code words by bit position, right? So if we have a code word that's, let's say 5 digits long, and then we'll have a whole set of different code words, right? And let's see how to state this. When we have just the K bits, right? We're going to have a set of K input bits that range from 000, let's say, to 111, right? And all those values will be represented. But when we start adding these redundant code word bits, what we'll see is that we're going to end up with a sparse set of code words, right? And so they won't all be accounted for. And the idea, kind of the fundamental idea, is that we're going to have certain set of code words, K bits, N bits long, that are valid. And then those code words that are not in that valid set indicate that there's an error, right? And if we compare all of our valid code words and look at the number of bit positions that are not identical with each other, that gives us this distance, right? So we take two code words, we look at bit position by bit position. If they're different, if one's a 0 and one's a 1, then we count that, right? And then we sum that up for all the bit positions in that code word. Then we look at every combination of the code words in the valid code word set, and we find that minimum D, right? And the larger that minimum distance is, the better the code will be, right? So that's the total number of differences between two code words by bit position. So an example here, two code words, 4 digits long, 0101 and 1100. So let's compare this. That one's different, so we'll count that as 1. That one's the same, so we don't count that. That one's the same, but that one's different, so we count that. So how many did we count? We counted 2, right? So it differs in 2 different bit positions. So we'll call that a Hamming distance of 2. A code has many code words and is characterized by the minimum Hamming distance between any pair of code words. The lower the code rate is, then for properly constructed code, then you're going to have a bigger minimum distance because you have more degrees of freedom to kind of have this separation of valid code words from each other. It'll hopefully become a little clearer as we start to see some examples. That Hamming distance for a code word, for a single code word, is relative to all the zeros in the code word, or the number of ones in it, and is called the weight. All right, so now we talked about a distance between two code words, but we can look at a single code word and kind of compare it to the all zeros code word, right? And now every time you have a one in that original code word, because you're comparing it to an all zeros code word, you're going to count that, right, as the distance. So the number of ones in that code word is going to be what we call its weight, right? So you can imagine that you're taking this particular code word, you're calculating the Hamming distance relative to the zero code word, but all you really got to do is look at that code word and count the number of ones in it, right? So mathematically, we're doing one thing, but in practice, just count the number of ones by digit in that code word, and that's what we call its weight, right? So a lower code rate tends to produce more distance, right? Because n is bigger. Remember, our code rate is k over n. So as we increase n, we're adding more and more redundant bits. That means that we have an opportunity to have kind of more space between valid code words. It's a sparser type of representation of everything, right? So a minimum distance of 2 means we can detect any single bit error or any odd number of bit errors. Just like if you did look at parity checks on data communications, you may have found that you could use a parity check to figure out, like you can count the number of ones in a input bit word, and you add a parity bit to either make the total sum even or odd, right? Does that ring a bell? I hope so. But when you do that, you find that you can detect one error, but if there's two errors, it will look correct to you, right? If there's three errors, it's going to look incorrect again, right? But you don't know which bit, or actually how many bits are in error, right? So a single parity check gives you that ability to check for one error. Now, in these type of codes, we'll say that the minimum distance of 2 between all these code words means that we can detect a single bit error, or an odd number of bit errors, but we cannot correct any, right? So we know that there was an error, but we don't know which bit in that received code word was an error. So we'll need a larger distance for that. All right, so if D is the minimum Hamming distance of the code, then we can detect up to T bit errors if and only if D is greater than or equal to T plus 1. And so we can correct up to T bit errors if and only if D is greater than 2T plus 1, right? So just some handy equations. We're not going to derive those, but it's the idea that if you have a particular D, let's say D is 3, right? Then how many bit errors could we detect? Well, you're going to solve this equation, plug in, what did I say, 3 there, and so 3 minus 1, as long as that's 2. So as long as T is less than or equal to 2, then we'd be able to detect the error, right? Conversely, we have this factor 2 here. So now let's say that D is, well, we'll stick with the 3. right? So if D is equal to 3, then we subtract that 1, that's 2. And then we divide by 2 to solve for T, so that's 1. So T has to be less than or equal to 1. Okay, well, it's less than 1, it's 0, and we haven't had any errors, right? But it means that if D is equal to 3, we can correct up to 1 error, right? Now, there's some relationships here. This is assuming that you've built an appropriate code, right? So we can detect up to T sub cap D bit errors while correcting up to T sub C if and only if. So we've got this equation here now, right? So it's just showing that we can correct some errors and we can detect some errors, right? So, all right. With the code rate of less than 1, we have more available bits to send the K bits of information, right? So this is that redundancy. It's just stating that we've got K bits that we want to get from the transmitter to the receiver. And we're going to send those, but we're also going to send these redundant bits, right? And the code words are these valid set of bits. If the received word is not a valid code word, then we know that an error has occurred. Okay, so now let's get into it here a little bit, right? So we're going to have a code word, and we're saying that that is n elements long, right? And we're going to have a message word D that's this K that's long, right? And now we're going to create our code word from our message word D via this G generator matrix. And this matrix is going to be sized K by N, right? And so a note, we can get all geeky and study Galileo's fields. And if you take a whole course on error control coding, then you would study these, and it's basically kind of deriving a math rules for a certain size of numbering system, right? But we're going to assume a Galileo's field of order 2. And so all our computations are going to be done in this modulo 2, where there's no carry from bit position to bit position, right? So we're not like adding in a conventional sense. We're adding modulo 2, which, does anyone remember what like logical operation that corresponds to? You remember a modulo 2 type of operation before? In maybe 229 or embedded systems or anything? Yep. It's an exclusive OR, right? By a bit exclusive OR type of situation, right? So we're going to designate it with this plus with the circle around it. So these are the rules. And we'll predominantly use the addition, but I'm including the multiplication, modulo 2 multiplication while we're at it here. So 0 plus 0 is 0. That makes sense. 1 plus 0 is 0. That one makes sense. But I'm sorry, 1 plus 0 is equal to 0 plus 1 is equal to 1. That's what I meant to say, right? So it's, what do they call it, commutative, and but they equal to 1. Here's where the difference occurs. 1 plus 1 is equal to 0. There's no carry. It's not equal to 1, 0 in binary. It's equal to 0. And you just throw away that carry. And the multiplication, yeah, it's a little bit straightforward. We have 0 times 0 is equal to 0 times 1 is equal to 1 times 0. Is equal to 0, 1 times 1 is equal to 1. So that one's conventional, or at least to our brains, it's conventional. It's just that this last one, which is like that exclusive OR gate that you studied, right? So we have this generator matrix. The matrix operation is a linear operation, right? You're multiplying elements in this matrix, and then you're adding them up. But all that is a linear type operation, right? Each code word is a specific linear combination of the message bits. Sum of any two code words is also a code word, and that comes from this linearity property. So if you take one code word and you valid code word and you add it to another valid code word, that should produce a third valid code word, right? The all zeros code word is also a code word in any linear block code, right? So you know at least 0, 0, 0, 0, 0, however many n zeros, that is always going to be a valid code word in a linear block code. Okay, so we're going to now talk about systematic codes, right? So most of the, at least conventional or more simple type block codes are systematic. What do we mean by that? It means that the message bits are present in the code word, right, in some block, and typically at the beginning, right? And then we tack on these parity bits, right? So there's going to be n minus, so this is k, that's n, so the number of parity bits is going to be n minus k, right? But so when you look at a received code word, if it's valid, you should be able to just throw away the parity bits. Boom, that's your message, right? You're only using the parity bits to make sure that there were no errors in this process, right? So that means that we can write the generator matrix. That the generator matrix is going to take this and generate that, right? And so we can write it as this identity matrix concatenated with a parity matrix. Okay, so I is the identity matrix with size k by k, right? So you're taking those k bits that are coming in, you're multiplying it by 1 to get k output bits, right? And P is the parity matrix with size k by n minus k. So we're going to take k input bits, we're going to multiply it by the smaller portion of the generator matrix, what we call P, the parity matrix, and it's going to output n minus k bits that we'll put in there. That whole thing will generate a code word. Okay, so what does that look like? Well, here's a systematic code. Okay, so we see that here in this generator matrix, we have an identity matrix, right? All ones along the diagonal, zeros everywhere else, right? It's a matrix version of 1. And then over here, we have the parity bits, right? And so we can write this as C, our code word, is equal to D, our input bits, our message word, multiplied by this generator matrix, right? Now we can substitute in this G with the k-dimensioned identity matrix and the parity check matrix, right? And then we can multiply this through, and D times identity matrix is just D, right? So we can put D there, and D times the parity matrix we'll write as DP, D times P, right? And then we'll introduce a little notation here where we'll put the parity portion of the code word we'll designate as C sub P. And it's equivalent to or equal to this DP, right? So that's just a notation notation change there, right? So here's a Hamming. Okay, so Hamming did a lot of work on these digital codes. So he's got a lot of stuff named after him. So we have the Hamming distance. Here we have a Hamming linear block code. And we're going to denote it as a 7,4,3, right? And what's that saying is that we're taking 4, k is equal to 4 input bits. We're going to have n minus k or 3 parity bits, and our overall code word is 7 bits long, right? So the arrangement of these, each row of that is defining your code, right? So and then I'm just repeating here, G is the generator matrix. So over here, if you take all of these input bits, right, from 0000 up to 1111, right? So every message word is represented here, right? So that's a complete set. Now we take that and we multiply that, all these words, we'll take that vector as D and multiply it by this, then we will end up with these 7-digit code words, right? So we'll have the all zeros code word. Here we'll have 0001111, and so on. Now note that this is not a complete set of words, right? This is the set of valid code words, but there's a lot of gaps in these, right? So if you get a code word that's not in this list, that means something went wrong, right? And now you can detect that there's an error if you receive a word that's not part of this valid set. And then if you work hard enough at it, maybe you can correct it. So, all right. So are we clear on that? I know we went through a lot of different concepts there. This is what it looks like to this point of generating a set of code words, right? So you could just put these in a lookup table, right? And in your system, every time you get a 1001, you just output a 1001001, right? Or you can do this calculation on the fly. Do it just this matrix multiplication. And really, all you got to do is these, right? Because again, if you go through this table here, we see, we'll just pick the 0101. We see in the code, there's a 0101 right there. That means it's systematic. That message shows up replicated in the code. It's because of that identity matrix, this identity matrix, right? You're just copying that over. So, all right. So if we're good there, then that's all fine and good. But now, how do we actually decode it, right? And in that decoding process, we'd like to be able to determine that there's an error, or better yet, be able to correct an error, right? So how do we do that? Well, we're going to take this C sub P, right? It's that parity portion of the code word, right? And we know that it's equal to the data coming in, the message, D, times the parity portion of that generator matrix, right? So we can go back here. We see that right there. This C sub P is equal to that DP. So now what we're going to say is that if these are equal and we do a modulo 2 operation, what should the result be? If you take two vectors that are the same and you do a modulo 2 bitwise operation on it, what should the result be? 0, right? Because they're going to match up at every single instance, and either if that bit position is 0, you're going to have 0 modulo 2 0 should produce 0. 1 modulo 2 1 should also produce 0, right? So bitwise, that modulo 2 operation should produce a 0 in every location, and of course that sums to 0. So your result should be 0, right? So we're going to say that that's what would happen if there's no errors, right? So now we can just kind of rewrite this, and this D times P moduloed with CP, we can rewrite as this little vector matrix multiplication, right? So we'd have D times P plus C times IM is equal to 0, right? And now note here, though, that this I sub M is a little different dimension than that previous identity matrix, right? On the generator side, we have an identity matrix, but it's dimension K by K. Here, this one's going to be dimension M by M, where M is this N minus K, right? So in that example, a Hamming 7, 4, 3, then N is 7, and K is 3, is 4. I'm sorry, and so you would have 7 minus 4 or 3. So M would be equal to 3 in that case, right? So now we can observe that D concatenated with the C sub P, well, that's just our code word, right? This is the systematic portion of it, and that's the parity portion of it, right? So that's equal to our code word. So we're going to take that, we're going to call that C, and we're going to multiply it by this, which we're now going to name H. Well, it's H transpose, okay, by convention. And so this C times H transpose is equal to 0, right? We just substituted in some things and renamed this matrix H transpose is equal to 0. So every valid code word satisfies this. Okay, and then so this H transpose is just this PIM. We call this the parity check matrix. Now, then you can undo the transpose, and H, just write H is equal to this P transpose. So we got to take the transpose of that times I sub M. Well, transpose IM is IM, right? So, all right. So now how do we actually go through this, right? So let's consider a received code word R possibly corrupted by noise resulting in bit errors, right? So now we have the code word that was transmitted was C, right? But now we're receiving a code word of R. We're also going to introduce this E, which is essentially the error vector, right? And in this case, we've got a 1 indicating where an error occurred. Okay, so if we take this C and we modulo 2, add it to this bit vector, we're saying that this error bit vector is causing an error in that particular bit position of the code word, right? So C is what's transmitted. Some errors happens in one or more bit positions. There's 0 errors, and it's trivial, right? So, but that technically, hopefully, happens most of the time, right? So C is then modified by this error vector, and what we're really receiving is R, right? So what we'd like to know is ultimately we want to recover like the D, right? We want to recover D. And we can do that if we can figure out what the true C is, or if we can figure out what this E is, right? Because then we could just kind of reverse this process and solve for C. If we know R, we received R, right? That's all our receiver knows at this point. But if we can deduce what E is, then we can use E and R and recover C. So, but let's go through it the forward direction first, right? So we start with a particular code word, a 1100, right? I'm sorry, I said code word. I mean a message word, right? So we receive, transmitter says, oh, I need to send this 1100 bit. So now I'm going to run through that generator matrix process, and I'm going to end up with a 1100, right? That's just copied over to the identity matrix, and a 011, right? So those are the redundant bits that we're sending along. Yes?
Is the 011 going to be the key?
Yeah, so, or it's the result of multiplying C times the P matrix. Okay, so yes, these are the parity, or it's the C sub P, right? So it's the parity portion of the code word, right? Now we're going to assume or examine what happens when in the channel there's some error that's produced, and by writing our error code word, error word like this, we're saying that the error is going to occur in this bit position, right? So really our received code word becomes C times E. So we have this E here, and we modulo 2. Did I say C times E? I mean C modulo 2 E, right? So we just take C modulo 2 E. So we'll have 111 0011, right? So our receiver is going to receive that. And now we're going to introduce this syndrome. Okay, remember we had in this previous slide here, we have this parity check matrix, this H of T. And we are saying that, well, a valid code word times this H transpose should be 0 if that's truly a valid code word, right? So let's go ahead and take what we received as a code word and multiply it by that parity check matrix. And let's see what a result is. Well, if we do this, we end up with 011, right? Well, it's not 0, so there must be an error, right? Because this ideally produces 0, right? But we know, well, now we know that we had an error in the system because we got a non-zero syndrome. So we call this S the syndrome. So we're going to use the syndrome decoding. S is not exactly unique, right? So we ended up with the 011 that says there's an error. We'd like to be able to take that information along with our knowledge of the structure of the code and figure out where that error was. Well, technically it's not unique. So we're going to figure out how we can make use of it, right? So what do we mean by that? S is not unique since R, that received code word, could be or can be produced by other combinations of C and E, right? So ultimately we want to figure out what C is or what E is. R is equal to the C modulo 2 E, but it's that combination that's producing our code word, right? So it's just not unique. We could have gotten that 011 syndrome that we got on the previous slide. We could have gotten that from some other code word modulo 2 with some other error vector. Okay, so that's a dilemma. What's our solution? Well, we're going to introduce this maximum likelihood rule and adopt this binary symmetric channel, BSC channel model. All right, so now this this gets back to our conditional probabilities, right? So we're going to say, and with this maximum likelihood rule, that this probability of receiving R, given that some code word transmitted C sub I, and that probability is going to be greater than receiving that code word for any other transmitted code word, right? So received code word, transmitted code word, we're saying that there's going to be one combination or one conditional probability that's greater than all the others, where K is not equal to I, right? That's that maximum likelihood. Now let's kind of substitute in here. So we're going to have a probability of error for a distance between code words, okay, and times 1 minus this error probability for n minus d, right, raised to this, right? So here we have this probability and this probability, you know, that's the remaining probability, right? So all your probabilities have to sum up to 1. So we can now rearrange this, and we can take this 1 minus PE to the n, and then this minus d, we can, right, if we have a negative exponent, that means it's going to be in the denominator with the positive version of it. So we've got, now if we move this to the denominator with this minus d, then we would have like exponents d, and we can group those together. So we'll have this p sub b in the numerator, and the d part of this 1 minus p sub b in the denominator, right? So so that's just kind of the derivation of it, and we end up with well, so this d is the Hamming distance between the received code word and the transmitted code word, right? And this P sub b is the digit error probability of this binary symmetric channel, right? So remember, there's that probability for each digit that's independent of any other digits that it's, and since it's symmetric, it can go from 0 to 1 or 1 to 0 with this equal probability P sub b, right? But if we have one error, so that probability would be P sub b. If we have 2 errors, right, then 2 bits in error, then that probability, since they're all independent, would be P sub b squared, right? If we have 3 of them, it would be P sub b cubed, right? So that's where we're getting this type of relationship here, right? So the key now, and this is the concept, right? So that's the math. That's kind of the derivation of it. But the concept is we're going to assume it's a reasonable, useful channel. In other words, that our error probability is less than 1/2, right? If it's greater than 1/2, then, you know, we're in trouble because so many of our bits are going to be in error, right? But if it's less than 1/2, then this conditional probability is a monotonically decreasing function of d, right? So if this is less than 1/2, then that's, let's say it's 0.4, right? So we have 0.4, then we have 1 minus 0.4 is 0.6. So we got a 0.4 divided by 0.6. Our denominator is bigger than our numerator, therefore it's less than 1, right? I think we can all accept that, right? So that's that condition less than 1/2, then this ends up being less than 1, right? And so then when we raise that to the power of D, it's going to decrease, and it's going to decrease monotonically, right? We're not going to have a little hump in it where we might have a local minima or local maxima or something like that, right? So to maximize the overall likelihood, we minimize the distance D. So we're choosing the that if we've received a particular syndrome, we're going to choose the error vector or the combination of this R and C that has a minimum number of bits in error, right? So we look at that error code word and we look at its Hamming weight, right? That's a number of ones in that error vector. And so if we choose an error vector with the minimum number of ones, the minimum number of bit positions, then that's the most likely outcome, right? The maximum likelihood, right? So corresponds to a minimum weight E. In other words, the fewest number of bits, 1 bits, which is also equivalent to, it's not a minus sign, that's just a pause, a dash, right? And that's equivalent to the fewest number of error bits, right? Remember, each one in that error vector represents a bit error. So we say that our C is equal to R modulo 2 our minimum error vector, right? So we are correcting R to produce our best estimate in a maximally likelihood way what our transmitted C was, right? Remember, we received R. We're going to figure out what this error E min is and use that to correct to get C. And if all goes well, now we've received a word in error, but we've recovered what was actually truly sent, and therefore we can actually also recover our data bits, right? So to correct the received code word into the sent code word, modulo 2 add the minimum error vector to the received code word. We typically generate a table of E min for each syndrome and then store that as a lookup table. So that's a little bit of a task you do. You do that as you're designing your code and you program it into your system because it never changes, right? You just program it hard-coded as a lookup table, right? And so for an exercise, you can take that Hamming 743 code that's on that earlier slide, and I think it's still slide 16. I probably should double check that, but you'll find it, right? So you can create, generate this lookup table of emin and then correct for a set of code words, right? So maybe that shows up on your final exam, right? So I'm not going to grade that homework. If you want to submit it to me and say, hey, am I approaching this right? That might be a good idea. But yeah, so that's something to do. Now your book is going to help you on this, right? But I've actually pulled in the example from a book, right? And so you can go to your book and see, look at now I know we're bouncing around in the book, all sorts of different chapters. Now we're way at chapter 13, right? So so here we have this generator matrix here, and I think this is a little bit different size than that 743, right? Because this is just six long, right? So yeah. So here we have our identity matrix, and then here we have our parity generator, the portion of the parity matrix. And so now we can calculate h of t from that, right? So here we'll have in this case, our m is equal to our k, right? They both happen to be 3, right? But in general, they're not necessarily equal to each other. It's just that n is 6 and k is 3, and therefore this m is also 3. So we put that identity matrix up there. We take the transpose of that parity check matrix, right? So here, that's that parity check matrix. So we have 1, 0, 1, and we'd have 1, 0, 1 in a column, right? And we have 0, 1, 1, right? And we have 0, 1, 1 in a column, right? So we're transposing that matrix. Let's do the last one. Our third row is 1, 1, 0, and our third column up here is 1, 1, 0, right? So you should be able to, from that, given that P portion of the generator matrix, be able to calculate this H of T, right? And then we can assume this binary symmetric channel and a maximal likelihood decision, right? And then we have R here. We're going to say is R10011. That's what our receiver has received. So what does the receiver do? Well, it calculates the syndrome, right? So we're going to take this vector and we're going to multiply it by this matrix, right? So we'll take 1, 0, 0, 1, 1, and that's going to be the first digit of our syndrome, and then we'll do 1 times 0, 0 times 1, plus on down, right? All in modulo 2 addition, right? So then you should get this result, right? 1, 0, 0. You can go through and I'd suggest that as you study this PowerPoint, you work through this example, right? And so given this received code word with this parity check matrix, you're going to get a syndrome of 1, 1, 0. So now our job is to figure out what E min is. Well, that's where you will have at some point generated these E min for a given S, right? And so these will be the minimum E's. Typically, you're going to see that, well, the 0, you're going to have the 0 error vector because there's no errors in that case, right? And then all these others in this case are going to be 1-bit errors, right? And then we'll have the last one, we kind of run out of 1-bit positions, right? So you see that this one is just kind of walking across. So every bit position is represented here. But we could get a syndrome of 1, 1, 1. And that we're going to say is corresponding to this 1, 0, 0, 0, 1, 0. Right? Kind of finding this one is a little trickier, and there might be another error vector that maybe produces the same distance, right? But you just pick one and map it there, right? So this means you've got 2 errors, so that's kind of bad to begin with, right? But all these others with these ones, you'll be able to correct, right? So in this case, we ended up with 1, 0, 1, 1, 0. So let's look up in our syndrome table. Where's 1, 1, 0? That's this error right here, error vector 0, 0, 1, 0, 0, 0, right? So 0, 0, 1, 0, 0, 0. So that's our error word in this maximum likelihood type situation, right? So it has that minimum weight. There's only the weight of this vector is 1 because there's only one appearance of a 1, right? So in this case, the weight is 2, but that's the smallest one that's going to correspond to that 1, 1, 1, right? So, oops. So we have this. So we take this, we look it up, we look up the error code word, and then we do this operation, right? We go back to our receive code word, and we modulo 2 with this. So we have a 1 modulo with 0, that's a 1, a 0 modulo with 0, that's a 0 modulo with a 1. Oh, we're going to correct this digit right there from a 0 to a 1. Okay, and then so on, it's 0, 1, and 1, right? So this is the most likely sent code word, right? Doesn't mean it's absolutely that. There could have been multiple errors, which would have corresponded to a different error, okay, error vector, right? And so, but in that sense that it's maximally likely that there was a fewest number of errors, then this is our C. Now, once we have the code word, we recall that it's a systematic code, so we can just peel off the systematic portion of it, right? Those first 3 digits, these are the message digits, those are the parity digits, right? So we just save this and we're done with those, so we can throw those away, right? So now we've received this, and we see that we would have naively just assumed that it was 1, 0, 0, 1, 0, 0, but it was truly a 1, 0, 1, right? So we corrected 1 bit in that process. Okay, so again, here's kind of the basis of it. If you run through the generator matrix, you should be able to take all these different code words. These are just kind of written in reverse order, and generate all these different code words. Then the little bit of a task is to create these minimums for each syndrome. Okay, and so in summary, our error codes can detect and sometimes correct some number of errors. I gave you a few formulas that kind of govern in this kind of context that we've focused on how to determine, based upon your minimum distance, how many errors you could detect up to, or how many errors up to you could detect versus correct. Right? A channel model is helpful in designing an effective error code. We assume this binary symmetric channel, binary symmetric channel. And again, go back and look at the definition of it, but it's a binary thing, and it's symmetric. So the likelihood of a 0 changing to a 1 is the same as the probability of 1 changing to a 0, and they're all independent. Each bit position has an independent piece of E, and they're all the same, right? And our code rate and Hamming distance are important metrics. And so you should understand what the implications are of those, be able to calculate a code rate, be able to look at maybe 2 vectors that I give you and calculate the Hamming distance between them, right? So again, you look at how many bit positions are different and sum those up, right? Count the number of bit positions that are different would be the Hamming distance, right? And a Hamming weight would be basically that operation with a vector against the 0 code word vector, or simply counting the number of 1s in a vector, right? So these are all important metrics in developing a code. In this case, computations, because we assumed a Galois field of 2, and I did not define what a
Gallows Field is, and I won't. It's a very advanced topic, and it makes my brain hurt. So I'm not going to make your brain hurt. It already hurts enough, right? So just understand that there's been some assumptions here that when you go and develop your own new code, let's say you want to do a PhD and you'll invent a new code that's a little bit better in some ways than any other code, and you'll get a PhD, right? So it's kind of hard though, because all the easy stuff's been done. Computations normally done using this modulo 2 math in these cases, right? And our syndrome decoding, what's underlying all that is that there's this maximum likelihood assumption, which kind of from a hand wavy standpoint is that you're going to assume that the error that occurred is kind of the minimum number of errors in that error bit vector. So it's the fewest number of ones. As we saw, a 0 means there's no errors, and most of those others in that entry only had a 1 in a position, and you use up all those positions, and then there's that, typically a last one that might have 2 bits in error. Okay, that's it. Any questions, comments, sarcastic remarks? All right, we will see you. It's been great seeing you all face to face. Unlikely I'll be back before the end of the semester, but you never know. I guess we still got about 6 weeks to go or something like that. I don't know. So yeah, and have a great weekend. And again, next week is one session, so no session on Friday. We ultimately need to make up a session, and so I will ultimately be recording a lecture, right? I think that was it the active shooter thing or something that they canceled class and stuff, right? So so I haven't done that yet. I'm deciding whether to maybe do that as your last one, which will be on AI, ML in radio communications systems.